Thank you, Mr. Alexandros Kanterakis. With good practices in using open source tools for reproducible science.
Right. Thank you. Thank you, the FOSSCOMM conference, for giving me this opportunity. I'm Alexandros Kanterakis. I'm a postdoc researcher in Fourth Institute in Crete. So this talk is about the replication crisis. I bet you all know about that. It's a crisis. It has affected a lot of science. Many people are talking about that. It's been on the mainstream media, etc. Now, what open source has to do with this? First of all, regarding the replication crisis in academia, it doesn't affect only low-level publications. There are like these publications in science, for example. If you just read the highlighted lines, you'll see that, we cannot reproduce this amazing high-profile paper because someone stored the computer on which the raw data were stored. These data were not backed up, and they were not deposited in an appropriate repository. This is another high-profile paper. It is from Science. Someone indicated that there is error, and they said, yes, sorry, I'm reading the last sentence over here, which says the researchers did have a script that they could have to fix this problem, but someone forgot to run it. This is in amazing high-profile papers, and it's happening very common. Regarding the reproducible, the replication crisis, first of all, it's not that funny. It affects a lot the science. It affects a lot the funding. Failures to reproduce data are followed by a 70 to 73 drop in NIH, and despite increased education levels, the public trust in the scientific community has been decreasing. It erodes the public belief in science. So I did a search a bit when I was completing this presentation, and I found that the very high-profile, the very well-known paper of Dr. John Ioannidis, which says most published research findings are false. It's very known, and if you haven't heard that, then you should make a note and Google it a bit later. And people that are climate skeptics, anti-vaccines, etc., they are using this paper as an argument against the scientists. They say, look, you should read peer-reviewed papers, you should trust science, you shouldn't trust, for example, your Facebook or your mainstream media. Read science. And climate skeptics and anti-vaccine people, they are using this paper and as an argument. So what I'm saying here is that this is, above all, it has eroded the public belief in science. But, so this is the one thing. Another thing regarding replication, because I'm trying to show different aspects and perspectives of this crisis, is as an academic, maybe some of you are academics, maybe of you are dealing with research. Has anyone of you spent weeks to install academic software, even if the code is open? Is anyone of you unable to reproduce a very simple plot from an academic paper? Has any of you tried to connect the output of a tool to the input of another tool with no avail? Maybe you had to move your data to specific directory structure and change the format to make a software happy? Or you had to downgrade your operating system or your libraries to meet specific requirements? Maybe you have this suspicion that the authors are making this tool unrunnable in purpose. Then it's not you. It does happen, and it happens a lot. So I'm in research like 20 years, and I'm listing here all the excuses from colleagues, friends, that they don't want to go open. And this is a list. One of this is no one. It's not a prerequisite for my institution. No one forces me to go open. I can build a career with very high-profile paper, very high index, without publishing my data. And my data is not essential for my work and my code. It's secondary, it's supplementary material. It's what the paper says, what matters. And my data is my own superior format, And no one, it's unusable to other users because I have compiled it in my special way. I don't have the budget, I don't have the money to adhere to open standards because this needs time, this needs efforts, and I don't have the time. And if I open it public, my data and my code, I will bombard it with emails from unknown people about, hey, how can you use it? You have this problem installing your tool. Oh, what's happening here? And the other one is that I'm doing a controversial science field, and I might be misunderstood. This actually has happened. It's a long list. Another one is that I don't know where to publish my data. I don't have a specific repositories. My data is like 2 gigabytes or 2 terabytes, and I don't have sufficient infrastructure. There are security or privacy issues. And some people say, oh, I am open, but it's in my closed institute, in my computer, in my own small silo, etc. Other excuses, there are many, is that my data and my code is not that interesting. It's not that good. No one cares about. The other is that it's unpublished work. It's under progress, etc. I cannot extract the data from a machine. I heard this excuse actually because it's in this peculiar database, in this peculiar machine, and I can't log in and dump the database, etc. Legal issues that forbid us. It's not actually mine. It's from a friend that no one knows about. I'm not sure my boss will be happy if I published it. It's incomplete. We are still gathering, polling, etc. And it's already published in my private repository. And some people, they are evading this question by saying data are available upon contacting the corresponding author. This is a very nice way of saying I'm not giving the data and I'm not giving the code. And what is, so if I make it open, what is it for me? So from all these excuses, what they really mean is I'm afraid I might be scooped and I want intellectual property. So the reason, or the main purpose of this talk is to persuade you otherwise. And okay, this slide's not showing very well, but anyway. So why you should go open as an academic? First of all, it's because it's 2020, and I shouldn't make any real strong arguments about that. It's about the culture of collaboration. It's about for sharing, which pushes you for improvement. You share your code, you will get comments, and comments will make you better as an academic. It will make you, it will help you build an online profile by publishing in repositories and in public databases, and you're gonna get. But the other one is about the dark matter of scientific output. So there is this company which is called DataCite, which collects citations, companies, authors, tools used in publication, has made this amazing graph on the right side. So it's a simple graph, it connects data and etc. And according to this graph, you see that there are 136,000 software. There are 7.5 million datasets. There are 14 million publications. If someone sees this graph, say, okay, oh, we solved any scientific issue by having 136,000 pieces of software. We have solved everything. Just pick the right one. But of course, the question is how many of them are open, how them are available, how many of them are installable, etc. And here I will argue that even if you're a selfish academic, like I don't care about science, I care about recognition, then you still have to go open. So, the reason why you have to go open is not only it's good for science, but because you have to. If there was a single slide about this presentation, then I would like to have this. First of all, many people, there was this paper from 2011 that was asked scientists if they think that data should be open. All of them, very high majority, said yes, we think that it should be open. They asked them, do you share your data? The scientist says, yes, we are sharing the data. Then they ask, can other scientists access your data? And then here you will see how low profile, how low percentages were these answers. So people think that they are sharing their data when they don't. So the European Union, I think there was before the first author, the first speaker, Mr. Tsavalopoulos, if I am correct, made some very nice comments about the current issues and the current policies in the European Union to promote open source, to promote open science, and to enhance reproducibility. I think the top of this is the FAIR initiation right now. FAIR stands for findable, accessible, interoperable, and reusable. And if you haven't heard that so far, then you will hear it a lot in the future. It's a set of guidelines on how to be findable. I'm not going to list them here. Most people think that FAIR means open data, but actually doesn't. FAIR shouldn't be confused with open data because you can be fair and at the same time require authentication and authorization for your data to be open. FAIR is about making clear what are the prerequisites to have access to your data, is to making your data available in repositories, even if you require some sort of permission, making clear about the format of the data, and making available the data in search engines. This is more or less what's the FAIR. But it's not only about the FAIR. FAIR is one. The second is about the EOSC, European Open Science Cloud. Maybe you have heard that about that. Now, the funny thing about EOSC, the thing that I know that, the thing that I enjoy the most, is that on the website, they try to define themselves by what they are not. It reminds me of these recursive, GNU acronyms, for example. So you say European Open Science Cloud. So you say, yes, we are open. So anyone can participate. It's not about science. For example, companies, private sector, etc., can also be there. It's not open. If you want to have it closed source, then it's fine. It's fine with me. And it's not the cloud like Amazon or Azure, for example. So, but it is like an effort from the European Union to collect all the academic mainly, but not only scientific efforts in a common interoperable workspace. So they do have this marketplace, and I think it's a really good idea to go there, and you will discover some amazing services that are there, and they are doing their best to connect them and create an ecosystem of software and services. But why do we have to be FAIR compliant, or why do we have to be included in EOSC? So this is from a proposal of the European Union, AI for Genomics and Personalized Medicine, and I've highlighted some text which says that the European Open Science Cloud Initiative, the EOSC, may facilitate researchers to the newest data managing technology, etc. So this EOSC and this FAIR is actually, it's becoming very serious, and it's starting to become a prerequisite for researchers in Europe. So the funding, the proposals, they are actually actively saying that you should be part of EOSC. The same thing happens with the H2020 program, the guidelines on fair data management in Horizon 2020. No more, no less, they are saying that good research data management is not a goal in itself, but rather the key conduct leading to knowledge discovery. So you have to make your data fair. This is from the Wellcome Trust. It's another funding body, and the top thing that says that we expect all output of research funded by us to be shared openly and as quickly as possible. And regarding fair efforts, there are many national efforts. For example, this is from the Netherlands on the left, from the Delft University, where they have published a national plan for open science. On the right side, this is from Ireland, where they have published also another national framework on the transition of an open research environment. And what really astonished me on that point is I looked deeply on the Delft University, because I happen to have my PhD in the Netherlands, and says at some point researchers are expected, I repeat, expected to have their data and code as to adhere to FAIR principles for at least 10 years. And if you think that this is happening in the Netherlands, then I think you are mistaken, because these trends are slowly, they're coming to Greece as well. So if you are a researcher in Delft, you are expected by your institution to have your data open under these FAIR principles. And this is the European Code of Conduct for Research Integrity, which also states that the research should be fair. So if you are not fair, you do not have integrity. This is where it goes. So it's not only Europe. On the top left is from the letter from the White House. It's from the Federal Register on the United States. From the lower left is from Australia, and from the lower right is in Africa. There is a worldwide effort to make these FAIR principles a mainstream tendency. And it's not only, of course, these funding agencies. It's also the journals that want open data code. This is from Nature results that says that a condition of publication in Nature Research Journal is that authors are required to make materials, data code, and associated protocols available. The same stands for BMC. And other Sirius conference, of course, they also want open data code. So there is this supercomputer conference where in 2018 they said that you are advised, but if you want to get a best paper award, then it's a prerequisite that you should also give us the code and an example or a minimum example of your experiment, that we should be able to run it. And other conferences, for example, the SIG, INDECIAM SIG conference, they also following these trends. So we might see on the future in the high-profile conferences, you do not submit your code. You don't submit only your paper, you have to submit your code. And another thing that astonished me is that, this again from Ioannidis, you will see on the right, that there is some suggestion about a penalty reward system. You are open, you are getting a reward. You are not open, you are getting a penalty. You do not get funded. It's like the other children, the neighbors are not going to play with you. But it's a very serious mandate that we should all take a look. So Ioannidis is proposing that several strategies may be useful, including routing, replication, public data and protocol availability, funding incentives, reproducibility rewards or penalties, and targeted repeatability checks. So we might enter in a system in the future where your reproducibility and openness will be a very serious criteria for the adjustment of your advancement of your career. So let's move to the second part of my presentation, which is about how to make source code, how to help your how to make your academic software all tool, not only open source. Open source, I think, is the rule right now in academic software. It's how to ease reproducibility, okay? And first of all, you have to make the source code publicly from day one. This is a common error that many people think. This is okay, I'm open. I will make it open as long as it's mature, as soon as it's mature. No, make it from day one, because this will help you track the project. It will help you build communities, attract community from early on, and it will allow you to check your reproducibility at the very early stages of your project. The second thing is that having your code in GitHub is not enough. I cannot stress it more than that. The fact that your code is GitHub doesn't say anything, okay? Because your discipline, your research discipline has built communities, and they have some really nice catalogs there with tools and formats and data sets, and it's a very, very good idea to publish it there. I have listed three here in astronomy, in bioinformatics, which is from the Elixir project, and from geosciences. So many people just publish code on the GitHub and they say, okay, I'm done with openness. No, there are many other repositories and public databases where you can publish your code or your data or whatever you are doing. And the number 3 that many people forget is adopt a license and comply with the license of third-party dependencies that your project might have. This is very important. A project without licenses is not an open project. Open project means a license that the community can follow. People will feel very awkward to contribute to a project without a license. Okay, and of course, define clear and transparent contribution, governance, and communication process. In your README file, just say a few things: who we are, what we are doing, for whom we are doing, what we want to do on the future. Don't just say, oh, this is a very nice project for fast Fourier transformation, or I don't know. How do you think about making this project? And things like that. People, open source community love listening things like this because make them feel like they are belonging more to a broader community. More concrete, add README and license. I already said that, but 23.6 do not have a license or README file on their repository, which is the main criteria for reproducibility. Another thing is that the fact that you have a GitHub repository doesn't make your code citable. You might have worked years in your code, but I don't have a way to cite it in a paper because there isn't any way to extract a citation from your repository. So there is this Zenoto service which you can connect your GitHub repository and make it and have a DOI which you can actually add to your paper, to add other people to add to your paper. Also use ORCID. It's a unique identifier for researchers. It can help you connect software, data, tools, papers, authors, all this together. It's your unique ID. It's like your ID, public ID. And of course, build Docker and singular images. Okay, this is on coding, but I don't want to talk about coding because all of you are really good coders over there, and you already know that. Another thing is that some people say my format it's in CSV, SPSS, MATLAB, JSON. I've already published this data. So these formats, it's okay, it's open, but it's not reproducible. The fact that you have your data in a CSV file doesn't make it reproducible. What does it mean, the columns? What are the rows? The same thing happens with JSON, which has more complex data. So not only publish your data, but actually describe what are the semantics of its element. And remember, bad code is better than no code. Publish your computer code, it's good enough. This goes for students that they are very reluctant at the beginning, say, oh, I don't want to publish this. This is bullshit. This is a very low level code. No, publish it, because it's a good exercise for you. It's a good experience for you, and it will attract other people to help you. Now this is some cool things that I have seen around. Cool things you can do with open scientific repositories. One of them is you can make your paper executable with a binder. You see here, you just paste your GitHub URL, and if you have there a Jupyter notebook, then you press launch, and bam, other people can reproduce and check your analysis. Not only that, you don't actually have to have a Jupyter notebook. Even if you have a repository with some code, CodeOcean and other companies can help you deploy it, can help other people deploy it in a cloud environment. It's very good to take a look on these examples. Another thing is that right now in OpenSUSE we have finally a very, very good set of tools to do science. What I'm talking is about containerization software, about workflow management systems, about workflow engines, about workflow ontologies, deployment environments, low latency database. All these are open, and it's about big data and very demanding science, and it's very good. And it's also in the philosophy of reproducibility and open science. Now I want to talk about the containers. This is the workflow management system. I'm going from the bioinformatics, but I'm sure in every domain has a workflow management system where, you know, data are objects, tools are objects. You can combine tools and data in workflows, and then you can combine workflows with workflows. It's a very nice abstraction. It really helps you to clear what's going on. And then you have workflow engines. For example, here is Airflow, where you can monitor, submit, pause, cancel your analysis. And you have the workflow ontologies. This is very, very important. You can design your workflows as directed acyclic graphs. It's very easy, actually. And then, if you do this with this CWL format, you can make sure that it runs in the majority of execution engines. And there is a software which is called Arvados, which takes this CWL and make sure that you can run this in Amazon EC2, Google Cloud, Microsoft Azure, PBS, TorqueSlam, etc. So the old paradigm in bioinformatics that you have a data, this is bioinformatics, that you have data, you have an in-house programmer, an institute cluster, you get the results. But of course, this is not how it works right now. Why? Because in my line of analysis, in my line of work, in research, we have pipelines, and this is how pipelines look like. There is, for example, a script that assumes that all days are before 2000. There is this ARC script that has a missing dependencies. There are this program that only runs on that computer that caught fire. Yes, this has happened. So it's very fragile. So we have to find this fragility. We have to fight this fragility with containerizing our execution environments, combine all components in workflows, and deploy these things in workflow agnostic and language agnostic execution systems. And open source, we can very easily use existing open source tools to do that. I might have like 2 minutes. Okay, so what I've done personally myself towards this line is this OpenBio.eu, which helps researchers to combine different workflows and tools. And so this is my last slide. So the whole idea is, if you go to this OpenBio.eu, is that you have a unified environment where you can publish your tools in Bash language. You can, for example, a tool is a set of Bash commands that download these tools, and then you can combine tools with other workflows into workflows. You can build your own user profile. There is a forum. You can add a reference. This is a unified approach. This is my personal, let's say, effort to contribute in this this fight against replication crisis. So I'm gonna skip very quick through the many cool things that you can do with OpenBio.eu. Which one of them is that you can have many execution environments plugged on this platform, and then you can choose. You can say, oh, I want to run this workflow in this execution engine, and then you have a resource monitor, and you can plug your favorite custom execution engine, for example, the Airflow. And it's all done for mainly users that have very low IT knowledge. It's about the user interface. This is about the people that have helped me to build this OpenBio platform. And of course, I want to thank the FOSSCOMM community, the FOSSCOMM conference, for bringing us together and allow us to share ideas. Thank you.
Thank you so much for your presentation. We don't have any questions, so thank you again for your time.